Today's lesson will be for an AP Stat class that looks at hypothesis testing against a known value. Our lab will focus on the question, is the average birth weight really 7.5 pounds? Now, if you Google what is the average birth weight of babies, you'll see that Wikipedia or whatever, the first value that comes back in a Google search says that the average birth weight is 7.5 pounds. So let's assume that we took a random sample of 36 birth weights. And we want to test these 36 birth weights against this known value of 7.5 pounds. How would we do this hypothesis test? Let's go through the steps. All right, so the first thing we have to do is we have to set up hypotheses. We're going to set up a null hypothesis, which is the hypothesis against the known value, the status quo, and the null hypothesis looks like this. It is an H with a little 0 down here. Sometimes people read it H0, sometimes people read it H0, and it has the population parameter, mu, and it's against always the known value. This is always given. And our alternative hypothesis is what we want to find out. We want to find out, is the birth weight equal to that, the status quo, or in our case, is it something different? Is it not equal to 7.5 pounds? Now, I chose a two-tailed test. We know it's a two-tailed test because I chose this sign not equal to here. I could have also chose a greater than or a less than. If I had done one of these, it would have been considered a one-tailed test. Now, how do you know whether to pick a one or a two-tailed test? You usually use values or information from the problem that you have at hand. For instance, if I was testing to see whether or not premature babies have an impact on the birth weights. So nowadays, with all of the fertility testing and things like that, and more premature babies being born because we have more multiples and things, has that in fact lowered the birth weight? Well, then clearly my question of interest is that the birth weight has been lowered. So I would choose to use the less than. So I don't ever look at my data first and choose the alternative hypothesis. I base this decision on my question that I am asking. And in this case, I just want to know whether or not this sample is different from. I'm not specifically interested in a particular subset of the population, for instance, like I mentioned, the premature babies or anything like that. So I am simply going to use this two-tailed test option. So this is step one, setting up your hypotheses. Okay, so now we're going to move into step two. We have our hypotheses set up. So what we need to do now is we need to figure out how far to take a look at our data and see how far our data differs from that known value. So let's look at step two. Step two, we examine our data. So we have our data. Now our data might look like this. Let's say we have 7 pounds, 4 ounces, and 6 pounds, 5 ounces, 3 pounds, 2 ounces, etc. Now, if you look at this, our real data is going to be given in pounds and ounces. But if you notice our hypothesis, it was 7.5 pounds. That was in decimal form. So I have to convert this to match that. 7.4 pounds is not, or 7 pounds, 4 ounces is not 7.4 pounds. 7 pounds, 4 ounces is not 7.4 pounds. Because in order to get from ounces to pounds, there's 16 ounces in 1 pound. So I need to take the number of ounces here, 4 ounces, divide it by 16 in order to get the decimal portion of this. So 4 divided by 16 is 1/4, or 0.25. So 7 pounds 4 ounces would actually be equal to 7.25 when I convert it to decimal form. So be careful that if you're given something in a different form, that you make sure it matches the way you are presenting it in your hypothesis form. I've had students do this before and they've just converted these incorrectly, especially with things like height, where it's 5'3" and they write 5.3. Again, you got to make sure these match up. So if we get all of that correct and we've converted all of our pounds and ounces to decimals and we put them into our calculator, and we want to find out the mean and standard deviation of our data. So we get, let's assume that we find out that our mean is 7.32, our standard deviation is 0.87, and we have 36 data values. Now, why did I use X bar and S for my mean and standard deviation rather than mu and sigma? Well, remember that these are the ones we use for sample, and these guys are the symbols we use for population parameters. So we want to make sure that we choose the right symbols and the right values off our calculator, because our calculator will give us both the choices of S and sigma. So pull the right values off your calculator. So I'm going to assume that you know how to put the data values into a calculator, like the TI-84 is a good one, and pull these values off your calculator. And now that we have this information, we need to figure out how close our mean is from the mean we're testing against. So to do that, we're going to do I think we're on step 4. Step 3 was to collect those summary statistics. I might not have written that down as step 3. But step 4 is to compare mu to X bar and to see how far away they are. If they're really close to each other, then there's no difference. If they're really far apart, then we know there is a difference. And we don't expect them to be exactly the same, as we didn't look at all values of X bar. We didn't look at every single birth weight. We only have a sample of them. So we're going to expect that there's going to be some difference here. We just want to see if the difference is enough to conclude that these values are the same or different from each other. So how do we compare these two values? Well, we compare these two values using a z-score. And a z-score tells us the number of standard deviations that these are away from each other. So to calculate that z-score, we take X bar minus mu, and we divide it by S over the square root of n. So that's what we're going to do now. So we're going to take our value of 7.32 minus 7.5, divide it by 0.87 over the square root of 36, which we know will be 6. And we'll put the answer to that on the next page. Now, keep in mind that that denominator, S over the square root of n, the reason we use that, if you remember correctly, is so that we're using being able to apply the central limit theorem, and that allows us to assume normality if our sample size is large enough. So that's a whole different concept, but that's an important one to know about. So our z value, once we do that math, comes out to be negative 1.24. And again, understanding this concept of z is really, really important to statistics, and it relates back to that normal curve. the normal bell-shaped curve. You have 0 in the middle, and then you have 1 standard deviation, 2 standard deviations, and 3. And you have -1, -2, and -3. And you can immediately know that anything that falls between 1 and -1 is completely average and normal and assumes no difference at all. So if I ever get a value that falls between -1 and 1, I can assume no significant difference right off the bat. Similarly, anything that's out here on these tails is going to be highly significant. That's really far away. So these are going to be significant without a doubt. So the question lies is what happens when we're in this range here? How significant are these values? So to do that, we have to use find the probability of these values, and we use something called the normal CDF. And again, our calculator will do that for us. So we use normal CDF, and we want to find the probability using normal CDF from -infinity all the way up to -1.24. And if we do that, we get a value of 0.1075. And this is called our p-value. And p-values are our values of significance, which tells us how significant our test is. And we generally look for values that are less than 5%. Again, it depends specifically on the things that you're testing and how important it is. If you're testing something that's medical that has a serious consequence, 5% error is not going to be enough. You want something even smaller than that. But this is basically the probability of making a type 1 error, the probability that you reject that null hypothesis when it was really true. So the probability that we reject H0 when we really shouldn't have, which remember H0 says that the birth weight was really 7.5. So H0 says this, HA says this, and our p-value is about 11%. So the probability, if we reject H0, the probability that we make a type 1 error, that we rejected it when we shouldn't have, is about 11%. So usually we use a cutoff of about 5%. Sometimes you might use 10%. Again, other times maybe 1%, depending on how important the situation is. In any case, we are greater than 10% here. So we are going to fail to reject. And again, that doesn't mean that we have said that this is true. It just means we don't have enough evidence to prove that it's false. So we're saying that we don't have enough evidence to say that our 36 data values are significantly different from 7.5 pounds. And that's the end of this lesson.